Okay, so I'm going to be going through today the 2013 exam paper, the higher level, question 9, paper 2. The sound is a little bit dodgy just on the first few minutes, but then it's fine then. So I don't know what I was doing wrong. But anyway, hopefully this helps and I'll see you all tomorrow. Okay, so we begin today with the question, shapes in the form of small equilateral triangles can be made using matchsticks of equal length. These shapes can be put together into patterns. The beginning of the sequence of these patterns is shown below. So we have term 1, term 2, term 3, so on. And we're asked to draw the fourth pattern. So a nice and easy question to get us started. Obviously, it's really important that we don't go wrong here. I'm just going to see here that the length of this one is 1, the length here is 2, and the length here, which means that for term 4, I must have 4 matchsticks in length. So 1, 2, 3, 4. And if I go back and I look at these ones here, I can see that this is this is 3, and then this is 2, and this is 1. So 3 matchsticks, 2 matchsticks, 1 matchstick. So I'm going to go along with that. If I have 4, the next thing is I have 3, the next thing is I have 2, and the next thing is I just have 1. And that really helps me, I suppose, just make sure I have everything correct. Make sure I have 4 here, and that I have 4 on the bottom. Okay, so once you've gotten through that, it doesn't need to be a masterpiece. You can basically do what you want then, just fill it in. Okay, and that's what I've got done. Just a quick check, 4 here, 4 here, 4 here, 4, 3, 2, 1. Perfect. And then 4, 3, 2, 1. Perfect. Okay, so we're on to the next part. Okay, so step 2, it says the table below shows the number of small triangles in each pattern and the number of matchsticks needed. So complete it. So in the first pattern, we have 1 triangle, we have 3 matchsticks. In the second pattern, we have 1, 2, 3, 4. So I have 4 triangles and I have 9 matchsticks. In the next one, I have 9 triangles. How many matchsticks? So count them up. Okay, and in the 9 matchsticks, I have 18. Sorry, in the 9 triangles, I have 18 matchsticks. And then in the fourth one, the one I've just drawn, I have 16 triangles, and I should have 30 matchsticks. So again, just taking your time, counting things out properly. Okay, so the next part is part B, and it says write an expression for n for the number of triangles in the nth pattern. So number of triangles, I'm looking at this section here where I've underlined the number of small triangles, and I'm going to try and find a rule for this. Okay, so if I look at that, I have the number 1, the number 4, the number 9, the number 16. So I'm going to try and find a general rule for this. Okay, so I've got plus 3, I've got plus 5, and I've got plus 7. Okay, so it's definitely not linear. So we'll go again. So I'm going to get plus 2, plus 2. Okay, I'm happy enough with that. It seems to be the second difference, which means, of course, this is a quadratic sequence. So important to remember. So I'm asked to find the general rule of a quadratic sequence. So I do know some things. I know that t to the n is equal to an squared plus bn plus c is the formula or the general term for a quadratic sequence. Sorry, so I'm looking for the rule. Now, what the a stands for the change. I know that the second difference, so 2a is equal to 2, therefore a is equal to 1, and that's going to help me a little bit. So I know term 1 is equal to 1, so if n was equal to 1, it would be an plus bn plus c equals 1. So my first term, or term would be 1 by 1, plus b times 1 plus c equals 1. So it's a little bit confusing this time because term 1 is actually 1. But in the next one, I'm going to be looking at term 2, so we'll see what that is. So that's going to give me 1 plus b plus c equals 1, and then I can go minus 1 and minus 1 on both sides. So b plus c equals 0. So I have my first simultaneous equation. The second one might be a little bit easier because now on the second one I'm going n equals 2, which is term 2, and that would be an, sorry, that should have been squared squared plus bn plus c. Term 2 equals 4. So just have a look at where I got that. So again, this was term 1. This is term 2. So term 2 is 4. And of course, term 2 is, my n then is going to be 2. So it's going to be 1 times 2. Remember, I got my 1 from up here. Plus b times 2 plus c equals 4. Remember that 2 is squared. So I'm going to again get 4 plus 2b plus c equals 4. 2b plus c equals 0. So now I have my two equations. I'm just going to do my simultaneous equations. So it's b plus c equals 0, and it's 2b plus c equals 0. So what I'm going to do here, I want to obviously cancel out one of those. I'm going to multiply one of them by minus 1. So I'm going to get minus 1b minus c equals 0 all over 2b plus c equals 0. They're going to cancel, and I'm going to get 1b equals 0. Therefore, b equals 0. So if b equals 0, what does c equal? And it will be b plus c equals 0. So 0 plus c equals 0. So c equals 0. So now that that's worked out, I go back to my t to the n. So my formula for a quadratic is an squared plus bn plus c, which in this case is, my a was 1n to be squared plus 0n plus 0. So in actual fact, it's just n squared is my general rule. Okay, so the next part of the question said find an expression or a rule for the number of matchsticks needed to turn the n-1 pattern into the nth pattern. So basically, right, when you have terms, you have term 1, term 2, term 3. At the very end, we have term n, but the one before that, we have term n-1. So what they're looking for there is the difference, really, or how many do you need to add to this term to get onto that term. So before we find t to the n-1, the only way we can find out any of the information that we're asked for is to find t to the n, which of course is the general rule. So we've got to find the general rule again. Here I've got 3, 9, 18, 30. So let's see what type of a sequence it is, and that will help me solve it. So I go plus 6, here I go plus 9, and here I go plus 12. Okay, not linear. Let's go again. Plus 3, plus 3. Okay, I'm happy enough. So it's a quadratic. So it's a quadratic. Again, our t to the n is equal to an squared plus bn plus c. So at this point here, guys, let's remember that the second change was 3. Therefore, a is equal to 1.5. Okay, so now I'm going to create my two simultaneous equations. So I'm going to go with term 1. So term 1, n is equal to 1. And it would be an squared plus bn plus c equals, and in this case, term 1 is equal to 3. So let's fill in what I know. I'm going with so a I know is 1.5. So it's 1.5 times, my n this time is 1 to be squared, plus b times 1 plus c equals 3. So that's going to give me 1.5 plus b plus c equals 3. b plus c equals 0.5 or a half. Okay, that's the first one. And then we're going to use the second term, so term 2. So n equals 2, so it will be an squared plus bn plus c, and term 2 this time is 9. So just, if you're not sure where I got that. So now let's fill in what we know, and we know that a is 1.5, so it's 1.5 times 2 to be squared, plus b times 2 plus c equals 9. You do a little bit of working out there and rearrange. Okay, and I've just noticed that this should actually be 1.5 there. So if I rearrange this bottom one here, I should 2b plus c equals 3. So I have my two simultaneous equations now. I can go ahead and solve them. If you go ahead and solve them, you should get your answer. Okay, and it should work out to be that your c is equal to 0 and your b is equal to 1.5. So now that we know that, we can finish everything off. So it's t to the n is equal to an squared plus bn plus c, which in this case will be 1.5 times n squared plus 1.5n, and then obviously plus 0. So the formula for t to the n here is going to be 1.5 n squared plus 1.5n. So again, let's go back to the question. We're actually asked, what is the difference? How many more matchsticks do you need to get from the second last one to the last one? So if I asked you, how many matchsticks do you need to get from the first to the second, you would say the answer would be plus 6. Okay, or for the second to the third, you'd say it's plus 9. So you do that really, you can find that answer by subtracting the second from the first. That will tell you how many you need. So exactly like that, we're now going to go here. We know what t to the n is. We're going to find t to the n minus 1, and then we're going to subtract the 2. So t to the n minus 1 is obviously going to be 1.5 times n minus 1, all to be squared, plus, and I should really have my brackets at this point here, all plus 15 times n minus 1. Okay, so let's do exactly that. Let's subtract them. So my first one is going to be the 1.5 n squared plus 1.5 n minus, okay, what have we got inside here? So if we work this out a little bit, we're going to get 1.5 n squared minus 1.5 times 2n. So you could say necessarily 3n there. And you can work on that out all together. And what you'll start to find is certain things start to cancel out when you've worked that out a little bit further. Okay, and certain other things start to be cancelled out. And then what you realise then is you're actually left with 3n. Okay, the next part of that question says the number of matchsticks in the nth pattern in the sequence can be represented by this function, an squared plus bn. Find the values of a and b. Well, happy days, we've already done it, didn't we, in the last question? A was equal to 1.5, and b, when we worked that out as well, that was also equal to 1.5. So that's nice and easy. We already had the work done there. Okay, so this brings us to the very last question. It says one of the patterns in the sequence has 4,134 matchsticks. How many small triangles would that give us? So all we're doing here, guys, is we're just trying to figure out how many small triangles would be in that. We already know our formula for the small triangles. T to the n is equal to 3, we might call it 1.5, yeah, 1.5 n squared plus 1.5 n. That is our general rule. So when does that equal 4,134? So first things first, I can see here that I'm looking to try and find n, but I've got kind of decimals here or fractions or whatever the case is. So I might actually multiply everything here by 2. Okay, and that might just make things a little bit easier. So I'll actually get 8268 here equals 3n squared plus 3n. Let's bring that all over. So we get 3n squared plus 3n minus 8268 equals 0. Okay, might divide by 3 there, make it a little bit easier. So I get n squared plus n minus 2,756 equals 0. This is, of course, a quadratic. What are our factors of 2,756? Well, obviously we don't know. So we will do our minus b formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. You work all of that down as far as you can, and you should get two answers. You should get either n is equal to 52 or n is equal to minus 53. Obviously, there won't be a minus because it's getting bigger. So the answer is n is equal to 52. So then remember the general formula then is n squared. So it'd be 52 squared. And so the final answer will be 2704 and Shinné.